Hi there. So we are going to talk today more about sampling distributions. Um, and we're going to talk a little bit of terminology, and then specifically we're going to talk about how to describe the sampling distributions regarding some bias and variability. So just as kind of a quick review or overview or whatever, um, let's talk about how we come up with a sampling distribution. How is a sampling distribution made? And we're going to review some terminology. So basically, let's say we have some population. So for example, let's say I have like chips, like, poker chips. And in my population, I might have 100 blue poker chips and 100 red poker chips. So 50% of my chips are blue, 50% of my chips are red. Again, this is the population. If I take a sample of size 20 chips from that population of poker chips, I might come up with 12 blue, and I'm up here. I might come up with 12 blue chips and 8 red chips. Or I might come up with, in my sample of 20, I might come up with 9 blue and 11 red chips. So my individual samples are not always going to have 50% red, 50% blue. Sometimes they might, but sometimes they won't, right? But overall, I would expect most of my samples to have close to 50-50. Could I come up with a sample of 20 chips and have only like 5 blue and 15 red? Yeah, I could. But if the population were really 50-50, that shouldn't happen too often. So anyway, if I take lots and lots and lots of samples of size 20 and record what proportion of those chips were red. So I have a whole bunch of p hats. So in this first sample, the proportion of red chips was 8 out of 20, or in other words, 40%. In my second sample, the proportion of red chips was 11 out of 20, or in other words, 55%. So if I repeat this, repeat, and I take lots and lots and lots of samples, and from each of those individual samples, I record the percent or proportion of chips that were red, and then I make a dot plot or a histogram with all those proportions. That gives me what we call a sampling distribution. So a sampling distribution is a distribution that comes from a whole bunch of samples, a whole bunch of sample values. And in this case, it's a whole bunch of sample proportions. So think about it. If the population parameter tells me that 50% of the chips are red, this sampling distribution over here, this purple, in the purple, should kind of make sense. Most of my samples, most of my individual sample p hats were close to 50%. A whole bunch of them were exactly 50%. Some of them were a little more, like 55 or 45%. And then you had some that were like 60 or 40%. And you did have some that were as little as like 15% or 25% or as much as 80% red, but that didn't really happen that often. So this sampling distribution, the shape and kind of what this looks like, should hopefully make sense to you. So let's revisit some terminology. The population distribution is there in blue. That's the population distribution. It's what did we have in the population? What are the values of the variable for all of the individuals? And then from that population, we took a sample, another sample, another sample, a whole bunch of samples. But this here in the green is the distribution of the sample data. So these are the individual samples. What actually happened in a sample? And then finally here in the red, this is the sampling distribution of the sample proportion. So remember, think about that terminology. It's a distribution, so it's the values of p hat and how often that those values occurred. So it's a distribution from a whole bunch of sample proportions. So that's why we call it a sampling distribution. So it's really important to keep all that terminology straight. So on your tests, on your quizzes, on the AP exam, if you misuse terms, you're going to lose credit. And if you say vague things like, for example here, the distribution, you're going to lose credit. We need to be as specific as possible. If we're going to say the distribution is approximately symmetric, well, the distribution of what? The sampling distribution is approximately symmetric. The population distribution is about approximately symmetric. What exactly are we looking at? So make sure if you have questions, ask about these terminologies and then make sure you're using them correctly. Okay, so we're rarely actually going to come up with a total sampling distribution. Remember, a sampling distribution contains all possible samples of the same size from the same population. So we're not really, not never, it's not that we never, but it doesn't happen often where we can really come up with all possible samples of size 10 or whatever it is. So instead, we just get a lot of possible samples of size 10, and we call it an approximate sampling distribution. So most of the time when we say a sampling distribution, it's actually an approximate sampling distribution. Once we have that sampling distribution, we can use what we know about SOCs, shape, center, spread, and you're going to need to be able to describe a sampling distribution. More to come on that. And then this last bullet, although there may be high variability from repetition to repetition of the calculation of a statistic from an SRS, over time there's going to be definite pattern of behavior. Meaning, if I go back here, I might take one sample and it might give me 80% red chips. And then the next sample might have been 25% red chips. So from one sample to another, I can have a lot of variability. But over time, if I take lots and lots and lots and lots of samples from this population, I'm going to see this pattern. And this pattern, it looks like the shape is approximately symmetric. It's centered at 0.5. And a little bit later over the next chapter, a couple chapters, we're going to learn some more formulas about how do we figure out what the the standard deviation and other things of the distribution is. So more to come on that, on the specifics. But basically, in this last bullet, there's a definite pattern of behavior. In other words, there's going to be like some kind of a shape, a skew, or some kind of symmetry or something like that. Okay, so a statistic that we use to estimate a parameter, so like an X bar that we use to estimate mu, or a p hat that we use to estimate p, is an unbiased estimator if, read this carefully, if the mean of its sampling distribution is equal to the value of the parameter being estimated. So in other words, if I have a sampling distribution, this is the same sampling distribution that we were looking at before, and if I were to find the mean of the sampling distribution, so the mean of all the p hats, and that kind of came out, let me try and rewrite that a little nicer. The mean of all the p hats. Notice I'm using mu because I'm saying all the p hats, so it's a population mean of all the p hats. This notation means the mean of the sampling distribution for p hat. If this is equal to the parameter being estimated, well, why do we take p hat? We take p hat to estimate the population proportion p. So if this is true, then we say that p hat is an unbiased estimator. Think on this for a second. In other words, what this is saying If we sample over and over and over and over, we are going to have lots and lots of variability. Sometimes my p hat might be 25%, sometimes it might be 65%, right? But when I have that overall pattern, when I do it lots and lots of times, it's centered at the population proportion value, which is 0.5. So p hat in this case is an unbiased estimator. So here's that notation we were just talking about. Now, in this case, with the proportion of red chips, we're talking about p's, p hats, right? So this is down here. But if I'm talking about a sampling distribution for a mean, then I'm saying if the mean of all the x bars is equal to the population mean, then x bar is an unbiased estimator for mu. And again, this notation here. This is the mean of the sampling distribution for x bar or p hat. Okay? All right, so in the sampling heights example, we created the sampling distribution of the sample range for samples of size n equals 2 from the population of John and Carol's 4 sons with those heights. Is the sample range an unbiased estimator of the population range? And explain your answer. So we're going to revisit this problem. If you remember, we made this sampling distribution for the range. So these are all the possible combinations of size n equals 2, so 2 kids at a time or 2 sons at a time, and we calculated the range of all their heights, right? And that's what you see on the dot plot here. So I basically have to take the mean of all these ranges, and if that's equal to the actual range of the population, then we can say that range is an unbiased estimator. Well, let's check it out. So the ranges that I got from my sampling distribution were 1, 3, 3, 4, 4, and 7. So if I find the mean of all those, I add them up, divide by 6, I get 3.67, right? Is that equal to the range? Take a look. Go back at your original data. Here's your heights. So the actual range was 75 minus 68, which is 7. Those two numbers are not equal. So therefore, the sample range is an unbiased, is biased, or in other words, it's not an unbiased estimator. So you could say sample range is biased, or you could say it's not an unbiased estimator of the population range. Okay. Now we talked about mean with the same example. So let's see, is the sample mean an unbiased estimator of the population mean? So same thing, in order to answer that question, we need the mean mu of all the x bars, and that needs to be equal to the population mean. So here in the dot plot, this was the sampling distribution for the sample means. So again, all the possible samples of size n equals 2 from the population, and there were 6 of them, 6 possible combinations. So these are all the sample means. And we take the mean of all the means. So all the individual means are listed here, 73, 71.5, etc. Add them all up, divide by 6, because there were 6 of them. So this calculation right here is the mean of all the x bars. The mean of the population, the original population data, I add up all the individual heights, divide by 4, and I get 71.5. So because the mean of the sampling distribution for the sample mean is equal to the mean of the population, or in other words, the value it's trying to estimate, think about what that means, that phrase there. The sample mean is unbiased. It's an unbiased estimator of the population mean. Okay, so ultimately, we're only going to sample one time. We're not really going to sample over and over and over and over. We want to make sure that our one sample is a trustworthy estimate of the unknown population parameter that we're trying to estimate, right? So we need to make sure that we're using a statistic that is an unbiased estimator. But here's the thing, even if we have an unbiased estimator, it doesn't guarantee that our one sample statistic will actually be close to the actual parameter value. So we're going to talk about sampling variability. We prefer statistics that vary less from the actual parameter value. So take a look at these two sampling distributions, okay? So if we're estimating the sample proportion of people who have watched Survivor, and we take samples of size n is equal to 100. So 100 people in our sample, we ask, do you watch Survivor? So sometimes the percent of people who watch Survivor is 25%. Sometimes the percent of people who watch Survivor is 40%, right? You can see this overall regular pattern. Now, if we ask the same question, but and from this, it's important to note that this is from the same population. But if we ask the same question to the same population, but now we only take a sample of size 1,000, what do we know about bigger samples? If I have a bigger sample, my sample should be more representative of the population, meaning my p-hats should be closer to the actual p-value, to the actual population proportion of people who watch Survivor, right? So in purple here, larger random samples tend to produce estimates that are closer to the true population value. There's still going to be sampling variability. Sometimes my p-hat, it might be like relatively high. Sometimes it'll be relatively low. Sometimes my p-hat will be in the middle, kind of like here, low, middle, or high. But you're going to notice the variability of the sampling distribution on the bottom is going to be much smaller than the variability of the sampling distribution up top, because we used a larger sample, and that larger sample essentially should be more representative of the population. All right, so this is just kind of like recapping what we said. It's not guaranteed that a larger sample is going to be a better estimate, you know, because even in a, let me go back, even in a smaller sample, you can still have, you know, p-hat values that are exactly equal to the p-value. So it's not a guarantee, but it's just more likely that you're going to get a better estimate of the true parameter. So the spread of the sampling distribution is called the variability of that statistic. The spread is determined by the sampling design. So how did I select my sample? SRS, voluntary response, all that stuff, and also the size of the sample, not necessarily the size of the population. And we're going to talk more on that. But we just saw, let's think about this last part here. We just saw that the bigger sample size, the more representative the data should be, so therefore we should have less variability, right? But also think about your sampling method, your sampling design. How did you collect the sample? If you use a voluntary response method, your data could be all over the place depending on what type of people are volunteering, and the same for convenience sample. Whereas if you pick an SRS, your data should be more consistently representing the whole population. So it's not about the size of the population, it's the size of the sample and what type of sampling method you used. So a quick rule of thumb, if the population is at least 10 times as large as the sample, the spread of the sampling distribution is approximately the same for any population size. And again, we're going to talk more on this. Okay. Remember, our goal is to estimate a population parameter. If we want to estimate a population proportion, so the percent of people who like survive or who watch, Survivor, we should use a p hat, the sample proportion. So let's collect sample data and find the proportion of people who watch Survivor from that sample. If we want to estimate a population mean, like for example, average height, average weight, the average mean year, or the average year, we should use the sample mean. So if I want to estimate the average height of a student in statistics, I would take a simple random sample of size 10 or whatever it is and calculate that sample's average height, their X bar. So I really like this visual here. To decide which estimator to use when there are several reasonable choices, you need to talk about and think about both bias and variability. So take a look at this visual here. In the upper left corner, you can see, think of the bullseye in the target. This bullseye is the population parameter value, whether it's a mean or a proportion or a range, whatever it is. So let's say it's a population mean, and those black dots that I circled here are all of the sample means. I mean, it's great. All the sample means are close to one another. They're very consistent. But do we want to use these sample means? They're so far away from the population, right? So in other words, I have low variability. They're really close together, but I have high bias. The center of these black, and let me try and make this a little more clear, but the center of all these samples is like right there. So that center is not close to the actual population value, which is the middle of the target, right? Let's look down here at C. So now we have an estimator with high bias and high variability. So look, the center of all these black dots, these sample values, is over here, way far away from the population value, which again, we're assuming the population value is at the center of the target. So it's biased, but also the points are really, the point estimates are also really spread out. The black dots are really spread out. So it's high bias and high variability. And then up at the top right, now all these sample values are kind of centered at the center of the target, aren't they? Like all those black dots are centered around the center of the top target. So if it's centered around the population value, we don't have a whole lot of bias, but they're kind of inconsistent. They're all over the place. So we have a lot of variability. So low bias, high variability. What do we want? We want to be as consistent as possible when we sample, but we also want our sample to be like accurate. We want it to be unbiased. So in part D here, if the population value is the center of the target, those black dots again are the sample values. They're pretty consistent, so they have low variability, and they're also centered right at that bullseye, so they don't have a whole lot of bias either. And that's our main objective. We want an estimator with low bias or no bias and low variability. So bias means that our sample statistics don't center on the population parameter. In other words, they're not accurate. So like in C and in A, those sample values were not accurate. We had a high amount of bias. But let's talk about precision now. In letter B and letter D, or I'm sorry, C down here, we don't have a whole lot of precision. In other words, our sample values are kind of all over the place. We have a lot of variability. We want high accuracy, in other words, no bias, but we also want precision, low variability. So accuracy is kind of like the bias, precision is kind of like the variability. So we want this bullseye right here. And again, just a warning, be careful using terminology. So you want to make sure that you're writing and saying what you mean to say. So a lot of students use those two words, accuracy or precision, incorrectly. If you know how to use it correctly, great. If not, don't use that terminology. Just explain it. So you could say something like, the sample means were all really close to the population mean. In other words, if the sample means we're all really close to the population mean, we're talking about precision, low variability. Okay, that is the end of the section. Thank you all so much for watching and have a great day.